All right. Our next speaker this afternoon is Amelia Zhao, who's joined us from Pomona College. Amelia has been working the summer with Shenggi, and she's going to tell us about their project together, the ISM properties of High Redshift O3 emitters in the TNG simulation.
Awesome. So thanks, Gwen. My name is Amelia. So today I'm going to be sharing about, as Gwen said, the interstellar medium properties of high redshift galaxies, and we're using the illustrious TNG simulation. So our overarching goal behind this project is to better understand the universe's first galaxies. So we kind of start with the epoch of reionization, or the EOR, which is an era of the universe corresponding to greater than a redshift of about 6.5. And during this time, some of the first galaxies and luminous sources were emerging and photoionizing the intergalactic medium, which had previously consisted of just neutral hydrogen gas. And this gives us insight into just the formation of the universe. So again, these are some of the first galaxies to ever be forming. However, as I think Bhavya said earlier, this can be a really challenging era to study just because of the distance of these sources. So there's a lot we still don't know about the structure and the physical properties of these galaxies. We're really excited to have a lot of kind of new observations of sources from this time. So ALMA is the Atacama Large Millimeter Array. It's in Chile, and it's currently probing the kind of millimeter lines of these sources. JWST has already seen a couple of galaxies, and it's probing the optical lines. So we already have a couple optical lines of high redshift galaxies from JWST. And SphereX is it's upcoming for June 2024. It's supposed to be an all-sky survey. It's also probing the optical lines, and they're also planning on looking at these high redshift galaxies. So from these, we're able to see, so ALMA, we're able to see O3 88 micron lines very strongly for over a dozen high redshift galaxies, while JWST already has data for O3 kind of optical lines for at least 3 high redshift galaxies as well. So from that, we're able to say that these O3 lines are a strong tracer for the high redshift galaxies. And from that, we want to know, what can these lines tell us about the physical structures of the galaxies themselves? So in order to do this, we created an O3 emission model. And our model actually incorporates all of the O3 lines, including the optical lines. For the purposes of my work this summer, I was focused on ALMA and the 88 micron line, just because there were many more data points from ALMA. So as you can see on the left, our model is pretty simple. It consists of a single source of ionizing radiation at the center of a spherical galaxy with uniform gas properties, such as a density and a metallicity. And from those 3 parameters, as you can see on the right, I have metallicity, a density, and an ionizing radiation rate, which is connected to the star formation rate. And from that, we're able to calculate a prediction of the O3 88 micron luminosity for some galaxy. So the advantages of the model so far are that it's very fast, so it's easy to work with. It's physically motivated. And from Shengqi's past work, we've found that generally it does have a good agreement with cloudy simulations, which are interstellar medium simulations. The disadvantages is that obviously it relies on many assumptions about the interstellar medium, so this is not really a good picture of what a galaxy looks like. They're pretty inherently clumpy. Radiation comes from many, many sources inside the galaxy. So we want to kind of come up with a better view of our O3 emission model. So the way we're going to do this is by incorporating our model with the illustrious TNG simulation. So this simulation is a large cosmological simulation of galaxy formation. It goes from redshift 127 all the way until the current day. And there's 3 iterations of this simulation. So TNG 50, 100, and 300 correspond with the different volumes possible for the simulation. So each of these correspond to the side length of the box size of the volume of the simulation. So 50 megaparsecs, 100 megaparsecs, and 300 megaparsecs respectively. So by incorporating our model into TNG, we want to answer kind of two big questions. So firstly, are there galaxies in TNG comparable to those observed by ALMA and JWST? So a problem that was in past literature that we were looking at doing similar work was that so they were looking at simulations pretty similar to TNG 50. And the advantage of TNG 50 is that it has the highest resolution. But our galaxies that we're looking at are pretty inherently rare because they have such high luminosity. So they weren't finding any kind of galaxies that were comparable to those from ALMA. And we're wondering, is that kind of a limitation of our model, or is it just because our sample size in the smaller box size is just too small to see these galaxies? And then our second question is kind of broader, but it's asking, what can applying our O3 luminosity model to TNG tell us about galaxy structure? So using the TNG, we're able to have many more data points for our parameters, so we can apply our model more kind of locally than we were able to with just the simple galaxy model we were using previously. So for this first question, are there galaxies in TNG comparable to those observed by ALMA? So what I did was I went through TNG 50, 100, and 300, and I used a snapshot that corresponded to a redshift of about 8 in order to best fit with the observations from ALMA and from JWST. And so I plotted SFR on the x-axis, the luminosity on the y-axis as calculated by our model. The green and yellow dots are the galaxies from TNG, while the red and blue kind of circles are points found from ALMA. And the black line is fitted to current observations. So as you can see in TNG 50, there are only kind of a few galaxies with a high enough luminosity to even be comparable with ALMA, and there's none kind of up here. While in TNG 100 and 300, there are many galaxies that have a high enough luminosity and SFR to be comparable with ALMA observations, so we can use those galaxies to apply our model to. So the answer to our first question is yes, there are galaxies in TNG. So next we wanted to move towards our second question, which is about applying our model to these galaxies. And in order to do that, so this is kind of looking kind of really broadly, and each of these points is a galaxy. So we're going to have to look inside just one of these galaxies to learn more about the parameters inside. And I chose a galaxy from TNG 100 because it was a good balance between a somewhat higher resolution and having the right parameters that we needed. So what I did was I went inside the galaxy, and I was looking at, they're called gas particles inside the simulation. And there were about 25,000 gas particles inside the subhalo. Of those, around 10,500 had any star formation rate. So on the left, I plotted, based on gas density, the star formation rate and the metallicity. And I did this because these are just the 3 parameters of our model. So this plot was a little crowded, so I made it into a histogram. So as you can see, the most points are in the low density, lower SFR region, which is pretty much what we expect from these gas particles. And now that we know these parameters, so I grabbed all these parameters from the simulation itself, or calculated from parameters given by the simulation. And now that we know these, we can use those to input into our model for each particle. So again, our question is, what can applying our 88 micron luminosity model tell us about galaxy structure? So on the left, this is just a scatter plot of kind of the coordinates of gas particles colored by SFR, and I only include the ones that have any SFR. Again, this is just a scatter plot, so that's why they're mostly lower, I think. And on the right, I applied our luminosity model to each point with some SFR, and I colored it by the luminosity. So as you can see, our luminosity model is a good tracer of SFR, which is exactly what we would expect. It also gives us a little bit of insight into kind of the physical properties of this galaxy. But overall, the answer to this question is we are not sure yet. So there's still a lot we can learn from applying this. And we also want to kind of plot this in a more observationally motivated way. So this is kind of just showing the data, but by plotting it in different ways, we can make it more similar to what we're seeing. And so finally, our next steps for this project. First off, right now, I've been only applying our 88 micron model to TNG. So our next step is to incorporate the optical model just in order to be prepared for this new JWST data. Secondly, we want to apply a gas density distribution to each particle. And so for that, right now, we're applying the model more locally to the gas particles, which is like helpful. But the resolution of TNG 100 is still like not even close to the resolution of like a single hydrogen molecule at all. And so using a single value for gas density for the whole gas particle is not very realistic because again, inside those, they'll be clumpy as well. So we want to use the value of the density in order to create a distribution, in order to calculate a distribution of O3 luminosity values. Finally, to improve the luminosity plotting, so to make it much more kind of observationally motivated so that it looks more like what we might see from telescopes, as well as incorporating different like views, so from different viewing angles, what this galaxy might look like. Yeah, thank you. So, do you have any questions?
All right, questions for Amelia?
This is a really broad question, but based on what you've done so far, do you know what differences you might expect for the optical box compared to the 88 micron application?
Yeah, that's a good question. I'm not really sure, like physically, what it might look like, because they're pretty kind of. The 88 micron is our simplest model, which is the reason why I chose it, and the optical ones are a little more complex. So that's a great question, and I think maybe that'll come from doing the work itself. Yeah.
Other questions?
Yeah, I was wondering, so like towards the beginning of the presentation, you like said that something was like Z equals like 126 or something. It was like a really large redshift. Yeah, this one. So I was wondering like the physical necessity of having such a large redshift, because you're also talking about how like the very far away ones are at like Z equals 6. So this seems like an extremely like really large number.
Yeah, that's a great question. So this isn't my simulation, so I didn't really create this myself. I imagine it would just be for like the starting, like they run it with like certain starting parameters of the universe. So by running it with different starting parameters at a really high redshift, then you kind of extend it out and then see if it, or create your simulation such that it correlates with current observations. But again, I'm more using this simulation that's already been ran by people that are not me. So yeah, I can only make guesses as to their choices about redshift.
All right, other questions for Amelia? All right, let's thank her for excellent presentation.